Good afternoon, Senior 2 students. We're still in Chapter 2, Lesson 3, Part 1, Metallic and Non-Metallic Property. At the beginning of the 19th century, a scientist called Berzelius was the first scientist who classified elements into two main groups, which are metals and non-metals, and he classified them according to their physical properties. With the development of our concept about the electronic structure of the atom, now we can differentiate between metals and non-metals in addition to a third group of elements, which is metalloids. Let's start comparing metallic and non-metallic elements. Metals are elements that their valence shell or valence energy level has less than half of its capacity of electrons. Non-metals, their valence shell has more than half of its capacity of electron. Metals have large atomic radius, which lead to small ionization energy and small electron affinity. The opposite for non-metals, they have small atomic radius, which leads to high value of ionization energy and electron affinity. Metals tend to lose electrons, so they are called electropositive elements. Electropositive elements, as they lose the electrons and changes into positive ions or cations. On the other hand, non-metals tend to gain electrons, so they are called electronegative elements, as they gain electrons and change into negative ions or anions. Metals are good conductors of heat and electricity. Non-metals are bad conductors of heat and electricity. Metals are all solids except mercury, which is the only liquid metal. Non-metals are found in solid states, liquid, and gases. The third type of elements, metalloids. They are elements that have metallic appearance but have the most properties of non-metals. They take the shape of metals but they have properties similar to non-metals with a little bit difference. The properties of metalloids. Number 1, they have metallic appearance and most properties of non-metals. Number 2, electronegativity of metalloids is intermediate between metals and non-metals. Number 3, electrical conductivity is less than metals but more than non-metals. Metalloids are known as semiconductors, so they are used in electronic devices such as transistors. Metalloids are boron, silicon, germanium, arsenic, antimony, and tellurium. And this is the location of metalloids in the modern periodic table. The graduation of the metallic and the non-metallic property in the periodic table. Let's start by the elements in the same period. Where can we find the metal, the non-metal, and the metalloid? The period began with the strongest metal of group 1A. So the metallic property appears strongly from group 1A, and as we move from the left to the right by increasing the atomic number, the metallic property decreases till we reach the metalloid. After reaching the metalloid, by moving to the right of metalloids, the non-metallic property starts to appear, and as we move from the left to the right, the non-metallic property increases till we reach the strongest non-metallic elements that found in group 7A of halogens. The graduation of metallic and non-metallic property in groups. Let's start with a group of metals. For example, we have here group 1A, alkali metals. We can observe that as we move down the group, by increasing the atomic number, the metallic character will increase, because as we go down, the atomic radius increase the ionization potential and the electron affinity will decrease. We can know the strong metal by how easy they can lose their valence electrons. So the easiest metal in losing the valence electron will be the strongest metal. So as we move down the group by increasing the atomic radius, it is easier for the metal to lose its valence electron. So the metal with the highest atomic radius will be the strongest metal. In non-metal group, the non-metallic character decreases by increasing the atomic number. So as we move from up to down in group of non-metals, the non-metallic property decreases, and this is due to the large atomic radius and low ionization potential and electron affinity. We will end the metallic and non-metallic property by these important notes. Number 1, highest metallic elements is cesium. The highest metallic element is cesium, which is placed at the bottom of the left hand side of the periodic table, and it also has the lowest ionization potential and the largest atomic radius. Number 2, the highest non-metallic element is fluorine, which is placed at the top of the right hand side of the periodic table, and it is the most electronegative nonmetal and the smallest atomic radius. Let's move to the sixth property, acidic and basic property. When an element combines with oxygen, they will form a compound called oxide, and we have three types of these oxides. Element oxides are divided into three types, which are acidic oxide, basic oxide, and amphoteric oxide. And now let's compare between acidic oxides and basic oxides. Acidic oxides are non-metallic oxide, non-metal element attached to an oxygen atom. It is called acidic oxide. On the other hand, metal plus oxygen form basic oxide. Acidic oxides dissolve in water, forming oxygenated acid, and because of this property, non-metallic oxides are called acidic oxides because they dissolve in water, forming oxygenated acid. For example, we have here non-metal oxide, carbon dioxide, dissolves in water, giving carbonic acid. Sulfur trioxide dissolves in water, giving sulfuric acid. On the other hand, basic oxides or metal oxides, just like sodium oxide or magnesium oxide, dissolve in water, giving alkaline solutions. Acidic oxides react with alkali, forming salt and water, but basic oxides react with acids to form salt and water. Acidic oxides do not react with acids. Basic oxides do not react with alkalis. Examples for acidic oxides: carbon dioxide, sulfur trioxide, and nitrogen dioxide. Examples for basic oxides: potassium oxide, sodium oxide, and magnesium oxide. The third type of oxides is amphoteric oxides. They are element oxides that react with acid as a basic oxide and react with bases as acidic oxide. Their way of reaction depends on the type of the substance they react with, and in both cases they form salt and water. We have here four examples for amphoteric oxides. Number 1, aluminium oxide. Number 2, antimony oxide, zinc oxide, and finally zinc oxide react with sulfuric acid. Of course, it will react as basic oxide because it has here acid, forming zinc sulfate, salt, and water. The second reaction, zinc oxide, but in this case it will react with alkali, so it will act as an acidic oxide, giving sodium zincate salt and water. Thanks for listening, Senior 2, and we will continue the lesson in the next video.